So, welcome back. So let's do this thing on these Newton's second law and uniform circular motion. So here's my visualization. I have a mass that's going in a circle. I have a mass that's going in a circle. It's got a tangential speed, tangential velocity at any instant. The circle's got a certain radius, and the centripetal acceleration's got a certain size. And so I consider a ball of mass m tethered, that means attached to a string of length r. The ball travels in a circle with speed v. The ball experiences a centripetal acceleration that points towards the center of the circle. The acceleration is caused by the tension providing the strength. And there's two equations I need to be comfortable with. AC equals v squared over r, and our old friend F equals ma. As a tip, no matter how I draw the diagram, I'll probably do a little diagram just to the side. No matter how I draw the diagram, my advice is that you visualize it. First of all, above, that's fine. But the real take-home is visualizing it from the side. And the trick is, it's easier on your signs if you put the mass at the left-hand side. Because then your AC is a positive AC and your tension force is a positive tension force. If you put it at the right-hand side, then you really should call those negatives. And if you call them positives, you've got to remember to call them all positives, even though they're pointing negatives. But you might remember some and not the others, so it could get a bit messy. You might look at your diagram and go, oh, that's a negative AC, and it's the only thing you call a negative AC. So you've got to be a little bit careful with it. So my advice is visualize it with the mass at the right-hand side, from the side with the mass at the right-hand side. I want to talk to you about this centripetal force and centripetal acceleration, because it's tempting to say, oh, there's a centripetal force acting on that object. That's what's causing it to go in a circle. And that's bad language. It may be bad language that works, or it may be bad language that doesn't work, but it's bad language. The analogy is, if you decide to go on vacation and you say, I'm off, so you go to the airport, there's nobody there who's going to give you money to go on vacation. There's nobody there saying, are you going on vacation? Oh, here's vacation money. It doesn't happen like that. You have to get the money from somewhere else to go on vacation. So it's salary, or it's money you borrowed, or it's money you robbed from a bank or something. You've got to get the money from somewhere else, and then you use it to go on vacation. And the same thing happens with this. You need to pay for that centripetal acceleration using a force that already exists in your system. It could be the tension force in a piece of string, could be the gravitational pull for the Earth and the Moon. It could be the friction force of your tires, between the tires and the road. It could be the normal force on a bank track. You need some force which has some component, if not the whole thing, that gives you an acceleration towards the middle of the track. And it may be that force has been used for several things. It may be not only is it paying for your centripetal acceleration, it's doing something else as well. Maybe it's supporting a bit of the weight. And so you got to be careful, because when I was a student, I remember I'd add in my centripetal force to the other forces. And so I'd end up with this centripetal force thing that was added when it is part, in this case, of the tension. It's just a debt. It's a debt. It's the amount that you need to make this thing go in a circle. It's not what you get for going in a circle. It's the amount of force that you need to make this thing go in a circle. So you've got to be real careful about that. And so I found that things that got smoother for me when I stopped talking about centripetal force and I only spoke about centripetal acceleration. And sometimes I'll multiply that centripetal acceleration by m. If the centripetal acceleration is applied to a mass, I'll multiply that, ma. But I try not to verbalize it as a centripetal force. Although in old homework questions, I think I sometimes still have it there. So, 4 possible situations: soap on a rope. There's a conical pendulum. The soap on a rope is like you're swinging something and it's flat. The circle is flat. You can do it vertically. You can do it horizontally. From a analysis point of view, the horizontal is simpler, although it's harder to achieve. A conical pendulum is where you're not trying to get it nice and flat. You're just trying to get it into a cone. So there's angular stuff taking place. If you're driving around a track and it's flat, then there's frictional stuff taking place. If you're going on a bank track, have you ever realized that when you're driving down the interstate, you'll go around a corner and you didn't change your wheel, you didn't steer? You're just in traffic and you just, ooh, we were on 275 going south, and now we're on 275 going west. And I didn't turn my wheel. And because those roads are specially designed so that if you're doing about the speed limit, your normal force will set up the right component of acceleration to give you the circular motion with that precise radius. They're incredibly well engineered. And in fact, there's an interesting point where around about the time of Jimmy Carter, so 1972, there was the oil embargo. I remember that well because I went to college in 72, and in 75 there was another oil shortage, and that's when I graduated. And so there were no jobs in Britain. It was like, you got a degree, good, go and sign on for unemployment. There's no jobs. And so that I wanted to stay on anyway, but even if I'd not wanted to stay on, I was going to stay on so I got a master's degree. And then that basically recession lasted through 76 when I graduated with my master's degree, so I didn't get a job in industry. In fact, I remember on the industrial sponsors saying normally we'd hire a few of you folks, but we're not hiring anybody this year. So it was like, so I did my teacher training, and then I wanted to go back and do the PhD. So I kind of got into graduate school. I kind of wanted to do it. I had a faculty member, in fact, the chair department was like, he decided that I didn't belong, and kind of like was a bit dismissive of me. And there was this one conversation we had where he made it very clear that he thought I should just, quit and get a job and go off somewhere. And I resented it. And so, to some extent, I wanted to do it for myself, but I also wanted to do it to prove that guy wrong, It's like, I remember there was a time with my PhD when I'd started industry, and my company was trying to persuade me not to write up the PhD, because all that meant was that I'd be more marketable. Didn't help them any. And I took all my research and put it in the trash. And I sat there for about an hour feeling this total relief. And then I thought, man, that's 2 years of my life. I'm not throwing that away. And I remembered this one guy, and I thought, no, I'm going to write this thing up. I'm going to show that guy. And I went down and got it out of the trash. And I quit my job like that next month. I quit my job and just got a job teaching in high school and just wrote my PhD. So sometimes when people have been mean to you, actually, it can be quite a motivation. But around about Jimmy Carter, there was an oil shortage, and basically they reduced the national speed limits to 55 miles an hour. And it seemed like it was going to go on for a long time. So some of the road construction was constructed to a 55 mile an hour design. Now, when they're going over the crest of a hill, they can't have a speed limit which is high and you not be able to see what's over the hill. You've got to be able to see your stopping distance for whatever speed you're doing. Otherwise, it makes no sense. You're going to be driving and just crash into things. So when the speed limit was 55, they could do more curvy bits. But when you go to 70, you've got to do more shallow bits because you've got to have a bigger stopping distance for 70. In fact, stopping distance for 70 is probably twice as far as 55 because of the half mv squared relationship for the kinetic energy. So it's a big difference. And by the same token, going around a corner, if the speed limit is 55, the banking you need for 55 is different from the banking you need for 70. And I have a old colleague of mine who got involved with, because then you end up with this hodgepodge of roads where everybody's 55, so it doesn't matter, but some's designed for 55 and some's designed for 70. And then 10 years later, they got rid of the 55 and went back to the 70 mile an hour speed limit. So you have this like hill, this extension, this section in the middle of nowhere that should be 70 because it's in the countryside, but should be 55 because it's been designed to 55. And that can cause some problems. There's some real issues about what do you do about that. If you make it 70, strictly speaking, you're not fulfilling the technical spec of the road. But do you want people to slow down to 55 in the middle of nowhere for no reason and then speed up again to 70? Makes no sense. So there's been some real issues about that. So these things are really well designed. If you go down onto 275 and you go through Malfunction Junction and you get off and you go underneath, there's bits where you can go underneath that, and you look at the banking on those bits of road, it's quite a steep banking actually. It's very cleverly done. Soap on a rope, it's just a ball on the end of a piece of string. It was, when I was a student, it was one of those holiday presents when you can't think of what to buy your mum, you buy a soap on a rope. And it's basically a piece of soap with a little lanyard on it so they could put it around your wrist. So if you're getting showered or if you're getting bathed, you won't lose the soap. It kind of like, it just doesn't slip out of your hands. If it does, it's on this little wrist thing. Yeah? And so I was watching Star Wars the other night, and what struck me was, you think the Jedis would have got the idea of having a little strap around their hands? Because they're always dropping their lightsabers, and it's like, just put a strap on it, and it's fine, But they never did it, so they're not as good as they think they are, So you get this thing, you can swing it round over your head, and it forms it. The problem with presents like that, just to warn you, because the problems with presents like that is if you can't think of anything to buy your mum, maybe your brother's car, maybe your sister's car, So my poor old mum one time got bath salts from every single member of the family. Because what do you buy your mum? I have no idea what my mum's interested in. So we all bought, what the heck, we'll buy her that. So she opened the first present, it was bath salts, and then she opened the second present, it was bath salts, and then the third one. And I know mine's bath salts. And she's looking, she's going, wow, are you guys trying to tell me something, And I went and got mine, I said, I'll get you something else. Because it was, and I never did that again. I'd try and buy my mum quirky presents after that were from me, so I didn't want anybody else to have the same present. So watch out for that. Anyway, so these are the four we're going to do. First one, a 2 kilogram ball is attached to the end of a 4 meter long piece of, so I'm going to do a little diagram down here. It's 2 kilograms. It is 4 meters. 4 meters. Tension can withstand is 80 newtons. What is the maximum speed of the ball? Okay, so I want to know the maximum speed, Vmax. And then I'm going to visualize it from the side. So here's my thing. Here's the middle. This here is 4 meters. This tension, the maximum this tension can be is equal to 80 newtons. It can be less than that. If I go slower, it's less than that. But if I go faster, if you go too fast, it's going to break. So there's my tension. I can't really draw my velocity here, so I'll do it like that and put it down as V. And then my mass, of course, is 2. So I've got all my information there. I've also got my AC, of course, there. So I say the sum of the forces, we need a direction, let's do horizontal, is equal to MA. And I know my A is centripetal acceleration, so this is MAC, just to be clear. And this is MV squared over R. Now I'm looking at my diagram for my forces. And I've only got one force, plus T. There's no, yeah, there's a weight to this thing, but the weight down is balanced by my normal force, and they're 90 degrees to my axis that I'm interested in, so there's no component. There's no force going outwards, so there's only tension. It's in a positive direction, is equal to the mass, and the mass is 2, times my V squared, well I want my V squared, over R, and R is 4. So V squared is equal to, and this gives me, well, the maximum force, the string can withstand a tension of 80 newtons. So 80 is equal to 2 V squared over 4. So then I say, well, V squared is equal to 80 times 4 over 2, which equals 160. So V is equal to the square root of 160. And please work it out, which is going to be square root of 160. Get my little calculator. Second square root 160 and 12.65. Let's do that. There we go. Got it. So, isn't it the same old, same old? I did my diagram. I visualized. I recognized my centripetal acceleration was a centripetal acceleration, so it's V squared over R, so I plug that in. I used Newton's laws. I let the thing unfold. Yeah. Cool. I'm going to skip that one because it's the same old, same old. It's for you guys to do, but I want to try and get through these, so I'm going to do this. A car moving on a flat horizontal surface. So here's my car. I'm looking down from above. It's a 6 kilogram car. Makes a radius of 2 meters. So 2 meters. It's a toy car, isn't it? Coefficient of static friction, mu s, is equal to 0.8. What is the maximum speed? Again, maximum speed. I don't have to ask you for maximum speed because I ask you for anything. Just got to give you one unknown. Could give you the speed and ask you for something else. What is the maximum speed of the car while going around the track? I know my AC is there. Again, draw it from the side. That's going to be 2 meters. This is going to be this is going to be FF. And this is going to be AC. And that's 6. And this velocity here is what I want. So there's a little bit of a thing there. Frictional force is what's paying for this circular motion. You know that because if you try and do this on ice, you will not go in a circle. So if I get rid of the frictional force, I no longer go in a circle. So it must be the frictional force that's paying for this thing. Why is it called static friction? Because kinetic friction is when something slides across the surface. So if you lock your wheels and screech your tires, then you're in kinetic friction. But if you're laying your tire down and it never scrapes across the surface, it's just laid on the surface, then as far as that tire is concerned, it's static friction. It's just been placed and lifted and placed and lifted and placed and lifted. So it's a different mechanism. And it turns out, of course, you want static friction because the coefficients are higher with static friction than kinetic friction. So I want to find the R, yeah. Okay. The sum of the forces equals MA. And we'll say horizontal, which equals MAC, which equals M V squared over R. Now I'm looking at this diagram and I'm saying, well, this is fine, but I don't know what that horizontal force is. So I need to find that horizontal force. And you can do it on this diagram or you can do it over here. 6 FF 60 equals FN. FF is equal to mu times Fn. FF is equal to 0.8 times 60. FF is equal to 48 newtons. So I can do a little side calculation to figure that out. I go plus 48. No, I'm sorry, I missed a step that I want to put in. So I can say FF is equal to mv squared over r. So then I say that's plus 48 is equal to, that's going to be 6 v squared over 2. So v squared is equal to 48 times 2 over 6, which equals, let's have a look, 6 is into 48, 6 eighths are 48, 8 times 2 is 16, so v is equal to the square root of 16, which equals 4 meters per second. Now, if it was on a number line or a vector or something, I'd worry, is it positive or negative, like we did for the, but this is a magnitude, it's just like it's v squared, it's just a magnitude, so it doesn't matter. And I hope I said, what is the maximum speed? I didn't say what is the magnitude of the maximum speed, but speed is a magnitude. Cool? Same problem, little bit of an addition. You had to find FF. You've got to work a little bit harder for it, yeah? That's that. Angular stuff. Okay. I'm going to draw my diagram. I'm going to draw my diagram like this. I'm going to draw it like that. I'm going to draw it like that. I'm going to say it's there. Again, I'm putting the mass to the left-hand side. It's a 6 kilogram mass. I know that there's a tension in that wire. That tension is paying for the centripetal acceleration, but I know that the centripetal acceleration is towards the middle. It's not along the wire, it's towards the middle. And I know there must be a weight down here. There's no normal force because it's not resting on anything. There's just a weight and a tension. And that's causing that centripetal acceleration, which points towards the middle. Okay? I know that there's a velocity. And do I give you the velocity this time? I do, don't I? I say that's 3 meters per second. What angle that the string makes to the horizontal, that's that angle. That's what I want to find. Now, in truth, when you ask for the angle of things, it's like, where do you begin? There's a million equations of an angle in. So It's not like I'm asking you for V and there's only, you know. So we're going to have to scratch our heads a little bit on this one. What I can say is that Newton's laws still apply. What do I know? So I have my mass is equal to 6 kilograms. My V is equal to 3 meters per second. My R is equal to 4 meters. The horizontal circle find the angle between the string and the horizontal. Let me think for a minute. I'm thinking, no, I should be all right. Okay. So I'm going to say the sum of the forces horizontal equals MA, which equals MAC, which equals MV squared over R. I don't know what the horizontal component of tension is, but I know it's T cosine theta. There's two forces. There's my T and there's the 60. The 60 has absolutely no component horizontally, yeah? But the T does. So let's resolve that horizontally. T cosine theta is equal to M V squared over R. Okay. I'm going to turn around and say, okay, well, that means that cosine theta is equal to mv squared over rt. Yep. And this equals 6 times 3 squared over 4 times t. Oh man, I don't know t. I could find this out if I only knew t. I can say two-step problem. Find t, oops-a-daisy, t using the sum of the forces vertically is equal to, the sum of the forces vertically, do they equal ma or do they equal 0? So which equation applies vertically? Newton's first law or Newton's second law? So does sum of the forces equal 0 or sum of the forces equal ma? Which is it? Why does the sum of the forces equal ma horizontally? What about that diagram tells you the sum of the forces equals ma horizontally? Sorry? So which question are you answering? Yeah, you're supposed to use that. But now, why do you know that? How do you know that?
Because you're solving for t.
No.
It's not moving up and down.
No, that's not true. I mean, it is not, but that's not the point. But you're very close. Just change your language a little bit. What is it not doing up and down? It's not accelerating. Yeah, it might be moving, but it's not accelerating. So remember, you draw your diagram, you look for an acceleration. You say, I'm going to say the sum of the forces equals ma in that direction. So that's why we said the sum of the forces equals ma horizontally, because the acceleration's horizontal, because the thing is going in a horizontal circle. So always look for the acceleration and say the sum of the forces equals ma in that direction. And then if you cannot solve it, go at 90 degrees to that direction. There's no component of the acceleration at 90 degrees. So you know the Newton's first law applies, the sum of the forces equals 0. So with statics, it's Newton's first law and Newton's first law. And with dynamics, it's Newton's second law and Newton's first law. You know, so that again, it's that same pattern we've been doing. So now we say, well, the sum of the forces vertically equals 0. And now look at my diagram. And I say, well, hold on. I have minus 60. And that's going to be t sine theta added to t sine theta is equal to 0. So t is equal to 60 over sine theta. So then if I substitute back in, let's go to a different color, purple. So then I say cosine theta is equal to 3 3s are 9, 6 9s, 5 9s are 45, 6 9s are 54. 54 over 4. And instead of t, I'm going to put down 60 over sine theta.
You wrote down 52.
I'm sorry?
You wrote down 52.
Oh, so, yeah. So, thanks. So then, if I look at this, I can say, oh, I'm going to run out of space if I'm not careful. So this gives me that cosine theta equals 54 over 240, and that sine theta goes on top, yeah? Yeah, is that right? We're dividing by 60 over cosine, over sine theta, so we multiply by the reciprocal of it, yeah? Oh, and let's take that, and that gives the cosine theta over sine theta equals 54 over 240. And what's a cosine theta over a sine theta? It's going to be a 1 over tangent, isn't it? So tangent theta equals 240 over 54. So theta is equal to tan to the minus 1 of 240 over 54. So theta is equal to, second tangent, make sure you're in degrees, 240 divided by good old 54. That's going to be 77.32, 77 degrees. So, a different diagram, but the same beginning. It's a two-step problem. Well, the other one was a two-step problem. If you think about it, we had to find what our FF was, so that's a two-step problem too. It's a little bit uncomfortable. Well, I don't know about a little bit. It's a lot uncomfortable when you first begin, because you have the unknown comes as a cosine and a sine in the same equation, so that's like a bit of a bear. But remembering that trig identity, you can say, you know, adjacent over hypotenuse divided by opposite over hypotenuse gives me adjacent over opposite, which is 1 over tangent. And it works out. Now, in truth, I could give you the angle, and I could ask you for the velocity, or I could give you the angle, ask you and the velocity, and ask you for the mass. I mean, I can play with these things. This is, in a way, the most involved question I can ask you about this. I can't really make it more involved than this. So this is about as hard as it gets. But it's not necessarily what you're going to get. So again, I want to dissuade you from trying to remember this by rote, and then I ask you something easier and you cannot do it. I want it so that you get the approach. I'm demonstrating the approach over and over again. I'm not teaching you a problem. And I know when I began, I'd learned the problem. But I think there's a certain charm in, by all means, learn the problem, but go deeper than that and saying, now, why did he do what he did? Why did he put the sum of the forces equals ma horizontally? What was the clue? That's the skill. It's not being able to do the math. The math is like, just the math. It's why he's saying the sum of the forces equals ma horizontally. So try and step back and say, why is he doing what he does rather than what did he do? Okay? Let's stop that there. And